Did you write these down? But you gotta create a great playlist. I don't know.
I do. Well, I do actually essentially have a grading playlist. If you go to, it's like what happens is, okay, I got to get this done now. Then it's, yeah, loud, aggressive. It's like, all right.
Like smooth jazz.
Like Metallica 1, I need that over and over. You know, things like that. Anyway, but then it's like, oh wait, now I want to think about it and write nice comments or things like that. All right, now we're going to go to acoustic.
When you're grading mine, rewatch your Shockers
I have a
game
very
when they
good-
were undefeated. But one grade mine, just watching old Shockers
Oh,
basketball
yeah.
games when they won.
Yeah, the KU-WSU game.
There you go.
It's on YouTube. So.
When you grade mine, you watch.
Questions? You get this whole, 4-day break. So
You're getting this up.
So
actually, yeah.
Oh, that's
Terrible
so
when
nice.
they
Are you just saying that because we're here? Or do you-
No, I actually love teaching.
Don't make him justify
He's
it.
being
No.
recorded.
All right, yeah, I'm recorded. Hey. No, I actually, for most people who are going to go on to teach mathematics and stuff like that, they ask like, what is it to be if you want to be a good teacher, et cetera, and it's like presentation skills and all these other things. Like no, like students like no, just two things. Just wrap it up in two things: love your students and love your subject. If you care about your students and you care about your subject, everything else. I'm a terrible speaker. Well, I'm pretty sure you'll work on it if you want your students to know math. And if you care about math, you won't answer this question. Well, why did you do that? I don't know. Just do what I told you. Or better yet, I was talking to Richardson about this one. There was a guy who's like, if he didn't know how to answer the question, his immediate response to the student was, well, that's a stupid question. And then just move on. It's like, I don't know how to answer that. That's stupid. And on we go.
But you said mathematicians, if they don't want to say something, they ignore it.
Yeah, we just ignore it.
You
All right.
being a true mathematician.
I'm hardcore mathematician.
I don't just ignore it, I don't know.
All right, so last time we talked about the idea of what does it mean to be the same. Obviously, we're talking about the integers for number theory. So within the integers of number theory, and we have the sameness, we can first talk about the easiest one, which is we all understand. We have equality. And there's a couple of interesting features about equality. This whole idea, again, 1 plus 2, things like that. We know what equal means, but there's properties that come along with it, which would be things like, if x is equal to y, and these properties not only hold for the ints, they also hold for the reals, right? And so we can do things like, oh, okay, if that's true, then I can do two things, like, x plus 2 is equal to y plus 2. I also could say that x times 4 is equal to y times 4, right? One of the properties of equality are you can add equal things to both sides. You can multiply equal things to both sides. And sometimes we'll have to think a little bit deeper about problems, and so we can use those sorts of properties, and the other properties are the ideas. Do you know what an identity is? Do you know what an inverse is? So I said if we could say problems like, can you solve amongst the reals, say that 3 times x is equal to 3 times 2. Right? Pretty trivial problem. What would you do? Just tell me, what's the first thing I should do? I don't know nothing about math. What am I supposed to do? What would you do first? Right, so how would I do that? All right, so we just said divide by 3. So you told me divide by 3. And so I'm going to divide by 3. I'm going to cancel like that, and I say x is equal to 2. Some people would say divide by 3, and they would write 3x equals 3 times 2, and they just simply cross out those and just say x equals 2, right? So sometimes people would do it that way, right? They simply cross out the 3's and say x is 2. We're going to leave that for a second and kind of keep in mind that word that we did. Now that was for the reals, and would this work if all those numbers were integers? Right, and actually they were, right? I have 2 and 3, that's all I see there. So yeah, this is like an integer problem, which is, real, but we did a div by 3. But a second issue that we might talk about was the idea of congruence. So we did the division algorithm, which I like to call the sharing algorithm, right? How do we share? And we talked about I could find the remainder and I can find the quotient by using the div or the mod, because that really is just write it in the appropriate form. What's the div, what's the mod as we go through it. And the idea of congruence is a new type of sameness. It's the idea of same integers. And what we'll do is we will call A is congruent to B under modulus, say, M. Okay, notation is A is congruent to B under modulus M. That's in parentheses, not to say that I'm taking mod n. It's under modulus M. So the entire descriptor of A is the same as B. What do you mean by same? I mean congruent. Well, what do you mean congruent? The entire thing is A is congruent to B under a modulus. In other words, I have two piles. I have a pile of A objects. I have a pile of B objects. M people show up. I'm going to say that these two piles are the same. Well, the definition of this is simply that if I would take the two piles and subtract their numbers, I would end up with a result that is divisible by M. Well, kind of sit there and say, okay, well, that seems like a really weird definition. Well, let's kind of play around with it for a little bit. What does this mean? I don't like, because I'm still in algebra mind, the algebra of ends, and rather than thinking of divides. If you go on to number theory, and you're going to take number theory, you need to start shifting your thinking up into the higher concepts of saying divides rather than always bringing it back to algebra. But I don't think it's like if A divides B and A divides C, A divides any linear combination of B and C, if A divides B and B divides, right? You go through these sorts of statements over and over, and we're always talking the word divides. Eventually we need to get there. For now, I'm not. What does this mean? The thing on the left is also called what? Factor or divisor. The thing on the right would be a multiple. Okay, what does this actually mean? Those are terms of the algebra. That M times K is equal to A minus B. Well, looking at that, it's pretty easy to say, well, wait a second. That's really kind of saying that's a time, sorry. That say A is equal to B plus some sort of MK, right? So really, I could go to, I have a little theorem and I just proved it. 2, congruency also means that A and B are a MK apart. This gets used a lot. So I would call two numbers congruent under modulus M if there's some sort of M apart. Another way I could do this is to say, the third thing is, if I would go to this and I would go ahead and ask if these two numbers are equal, I should be able to take the modulus of both sides, and it should still be equal. I would take the mod of the left side. So I would take A mod M, and I took B plus MK mod M. Well, the left is just simply going to be A mod M. I don't know what the remainder is, right? That's just the remainder. But the right-hand side, I can do a little work. What do I have? I have two piles. I have a pile of B stones and a pile of M times K stones. M people show up. So they can go to the first pile and then go to the second pile, right? So if he goes to the pile of MK, there's M times K. All right, 5 times 4. There's 5 kids. So if I have 5 times 4 stones and I have 5 kids, then every kid's going to get 4 stones, and what's the remainder always? 0. M times K mod M is simply going to be what? 0. There's no remainder. So what's going to be left? Well, whatever B mod M is. Well, that's my second one. A mod M is equal to B mod M. So one must be a definition. These 3 all mean the same thing. One has to be the definition. The two are just simply restatements of it. There's a different way of writing it. They all mean the same thing. And all of these all mean that A is the same as B under congruency modulo M. I like to use my notation, and I'm going to use this from this point on, is going to be A is congruent to B modulo M. I like the bottom because it gives you a much better understanding that these are sameness, right? It's the same measure. A is the same as B, mod M. All right, let's have some examples of same. So is everybody okay that, notice how I do a whole lot of means? What does divisibility mean? Divisibility means that the left times the nth is the right. That's what it means. All right, what does congruency mean? Congruency means that if I subtracted the two numbers and would divide it, it also means that if I take a number and keep adding m, it's the same number, according to congruency. If I would take the remainders, take this number, divide by m, it means share it amongst m, take this number, share it amongst m, they have the same remainder, I would call them the same numbers. But what is my measure of same? My measure of same is the idea of congruency, this definition. All three are the way of talking about congruency. We would just pick which one you like best in terms of the problem we're considering. So, an example would be something like this. Let's say I'm looking to say under mod 5. Under mod 5, I'm going to take the number line 0, 1, 2, 3, 4, 5, 6, dot, 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 -1, -2, -3, -4, -5, and -6, dot, dot, dot. I'm going to take this entire number line and I'm going to go from here to here by doing mod 5. What is 0 mod 5? 0. Everybody gets nothing, nothing left over. What's 1 mod 5? 1. What's 2 mod 5? 2. 3 mod 5? 3. 4 mod 5? 4. 5 mod 5? 0. Everybody gets 1, nothing left over. 6 mod 5? 1. All right, what's -1 mod 5? I owe $1, 5 people are here. I'm going to collect $1 from everybody, pay the bill, and there's going to be how much left over? $4, right? -1 mod 5 is I have a bill of $1, I have 5 people. Take $5, right? $1 from every person. I have $5 in my hand. I pay my bill of -1. I have leftover $4, right? That make sense? What's -2? 3, -3, 2, -4, 1, -5, 0, 4, dot, dot, dot. Anybody notice a pattern? What do I notice about congruency? What I notice about congruency is who is 0 congruent to modulo 5? What is the definition of congruency? Probably this definition is one of the easier ways to think. Just keep adding 5. Keep subtracting 5. That's all that does. That's an easy way to think about it. All right? I could look at, well, who has same remainders? Well, that number and that number and that number, those all have the same remainder, right? So therefore, 1 is 6, which is 11, which is 16, which is -4, which is -9, which is -14, which is -19. What do I mean by is? Congruent. That's my new measure of same. So everybody here just simply is 5 apart. That's 5. Hey, that's the same as 10. By the way, that's the same as 15. By the way, that's the same as, everybody catch the pattern? Under mod 5, the number 0 is the same as who? How many integers are there? There's an infinite number. But all of these multiples of 5 are all the same as 0. Right? Who's the same as 1? 6. And 11. And keep on going. What about the other way? -4. And -9. Is everybody okay that these are all 5 apart? Add 5, subtract 5. All right, who would be 2? Who is 2 congruent to? 7 and 12 and etc. What about the other way? Start taking away 5. -3 and -8. Can you see why I changed my notation? Could you imagine having to write mod 5, mod 5, mod 5 over and over again? I'd have to go, oh, look, put 5 underneath it. Okay, I could go, if 5 is the same as 0, right? The fundamental groups are going to go down to who is 3 the same as, and what would be the last one? 4, right? Who is 4 the same as? 9 and 14. What about the other way? -1 and -6. And then, well, the next number would be 5, but 5's already known. So guess what? What does congruency do? Congruency takes your infinite amount of numbers and say that, wait a second, they have 4 unique blocks. Remainders of 1, remainders of 2, remainders of, whoops, I need to count right. This is the remainders of 0, these are the remainders of 1, these are the remainders of 2, these are the remainders of 3, and these are the remainders of 4. Every one of these group blocks, the entire first block are the guys who have remainders of 0. The second group are all the guys who have remainders of 1. They are all 5 apart. How could I tell? What's 11 minus 9? Sorry, other way. 11 minus a -9. I forgot to use the word negative. I pointed at negative. 20, and is 5 divided by 20? Yes. Why? Because this is a multiple of 5 apart. There's so many 5s in between. So here's the fun part. That every one of these numbers is the same for any one of these blocks, right? The first block, for that block, for infinity to both directions. 0 is the same as 100, which is the same as 90, which is the same as -1005. Those are all congruent under my new word of same. Here comes the fun part. What are some properties of same? All right, we already had the equality. Under equality, I had things like, hey, look, if x is equal to y, then x plus 2 is equal to y plus 2, and 2 times x is equal to 2 times y. You know, these are okay, right? These are correct. Those are still logical. What can I do with sameness? Add the same thing, but my sameness is equal. That means it needs to be 2. If the left side is 2, the right side must be 2. If the left side is a multiplication by 2, the right side must be a multiplication of 2. Here comes the fun one. What about congruence? What if I tell you that x is congruent under modulo 5 to y? Well, what am I allowed to do? I can add the same thing to both sides, right? Is that allowed? I put a 2 on the left and a plus 12 on the right. Is that okay? Why? 2 is the same as 12. It's like, oh. Why? Because they're the same. Right? Well, what if I said 2 times x? Guess what? It is 12 times y. Why? 2 is the same as 12. In other words, we have the following property. in terms of these examples. Those two examples of sameness. The reason why this is the reason why this is an equivalence, this is the same thing, is it meets certain definitions. When we take discrete 2, we'll explain why it actually is the same. There's rules. If I call something the same, and it can only be the same if it meets certain features, which is reflexive, symmetric, and transitive, but we don't know what those are. Anyways, so they are a same. They're a measure of same, but the theorem behind this particular property is if you have two objects, say x and y modulo m, and say a and b modulo m. And so both of these are obviously, these are all under mod m, right? If you're not talking about the same modulus, this makes no sense. But if they're both under mod m, then we can do the following. One, I can add the same things to both sides, which is what I just did. You look at it and say, well, you added something new. No, a and b are the same thing. So I just add the same thing to both sides. I can also multiply. The same thing to both sides. But now the measure of same is a large block of possible numbers to pick from. Equality was easy. Equality is, you bet, if the left is 2, the right needs to be 2. Congruence opens up the world. And it says things like, oh, okay, if I put a 2 on the left, and I'm talking modulo 5, what possible numbers could I put on the right? -8, -3, 2, 7, 12, 17. Any one of those. Why would I pick one or the other? That's an interesting question. Why would you? If I multiply one side by 4, what could I multiply on the other side? A -1, a 9, a -6, a 14, or 4. Right? They're all the same. Here's a more fun one. What if I multiply by 1? 1 changes nothing, right? That's an identity. But multiplying by 1 is the same as multiplying by what? 6, 11, -4. Wait, so if I multiply by -4, the number doesn't change? Nope. That's an identity. So how many identities do we have? An infinite number. Normally, which do we pick? 1, because they're all the same. So normally when we say, yes, there's an infinite number of answers, let's pick the smallest positive. If you're going to write one down, write the smallest positive, because there's an infinite that you could pick from. Kind of interesting that there's an infinite number. This entire block, all of this, every one of those numbers is an identity. Under mod 5, they all do nothing. They leave the number alone. All right. Why did I even mention that? Back to real numbers. If I ask you to solve 3 times x equals 3 times 2, and you said, well, I divide by 3 and I cancel both of those, right? I just cancel that 3 and x is equal to 2. And I say, time out. What did you really do? You say, I divided by 3. No, you did not. What you really did is say, oh, 3 has a multiplicative inverse that happens to be, what? 1/3. What you really did is take 1/3 to both sides, which requires a division, 1 divided by 3. Apply it to both sides. Why can you apply it to both sides? Because one of the properties of equality are you can put the same thing, and it has to be exactly the same thing because it's equal, to both sides. Why did I want to do that? Because those two together are 1. Whoops. And 1 is the identity. That's what you really did. What you really did is, oh, wait. My operator's multiplication. What's multiplicative inverses so that I can get the multiplicative identity of real numbers? All right, let's go to number theory. We're looking only at integers. And I write 3 times x needs to be congruent modulo 5 to 3 times 2. What is your temptation? Cross the 3's. And the answer is, well, how did you do that? What are you supposed to do? I need to I can't, if somebody says I divide both sides by 3, I at this particular point say that you just told me blah-de-blah-de gobbledygook. I don't know what you said. Why? Well, what do you mean? I said divide by 3. Do integers have a division operator? You just told me that you were going to, oh look, 3 times x equals 3 times 2. By flossa nasa nihilipilification, 3's go away. That doesn't make any sense, right? You just made something up. So that's my favorite long word, sorry. All right, div by 3 has absolutely no meaning. So what am I supposed to do? What I'm supposed to do is say what times 3, and I'm going to put it on the other side as well. And what's my hope? That better be 1. But same as, which means congruent as. If you think equality, this is really weird. Because guess what? What must that object be? Really? Because 1/3 is a real. But is 1/3 an int? No. So the only numbers that I could possibly plug in here are what? Integers. What integer times 3 is the same as 1? Scratch, 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 scratch. Well, here's what I'll do. Dun, 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 dun. Let's look at all of the same as 1s. What number could I multiply 3 by so I get one of the numbers who are the same as 1? 2. What's 3 times 2? 6. Is 6 the same as 1? Yes. So by observation, I can say, wait. I know that 2 times 3, which is 6, obviously, but that's the same under modulo 5 to 1. Okay, I'm going to put 2 on both sides. 2 times 3 times x is going to be congruent to 2 times 3 times 2. Why did I do that? Because 6 is actually 1 under modulo 5. So what did I multiply the left-hand side by? 1. So I have x is congruent to what? What's 2 times 3 times 2? That's 12. So that's a 12, but I don't like that. What is 12 the same as? 2. Which is, if you just look by observation, isn't that pretty obvious? It's supposed, for this one, and here comes the question is, the hard part of these problems are, this one canceled, right, but they don't normally. You're going to get these issues of a couple of things. 1, 2 is 3's inverse, modulo 5. Like under real numbers, 1/3 is 3 inverse under multiplication of reals. But if 2 is 3 inverse, all right, let's go back to here. You told me 2 was 3's inverse? Yes, I told you 2 was 3's inverse. Well, what are some other things that are the same as 2? All those. So how many inverses does 3 actually have? An infinity. I could have picked 2, I could have picked 7, I could have picked -3, I could have picked 12. All of those are 3's inverse. Normally you pick the smallest of the positives because those are useful. All right. This also doesn't get to the issue of, does everything have an inverse? No. Right? This entire block is an identity. These are basically, these are the identities for this block here. Identities under mod 5, right? Those are all the mod 5 identities. Every one of those numbers are a do nothing underneath. Sorry, should have said the word. The multiplicative identities under mod 5. That entire block is multiplicative identities. But the thing is, it's actually not true that all things are going to have an inverse to form one of those numbers. It's like, but I have an infinite number of them. It's possible that you would never get an integer times an integer to ever equal one of those. And so we still have to go if I'm going to do problems like, say, this, solve that, right? I have to have inverses to be able to form identities, to be able to go through the entire problem. If we're going to do solving of problems of this nature, we're going to have to say, when does an object have an identity and when does an object not have an identity? We don't have enough math yet to do that. So, aren't congruency samenesses more fun? Are they broader? You have all these lots of fun things that we can do. What's actually kind of cool about it, though, is for these particular things, we have an immediate corollary for that, for this feature, and the corollary is this. If somebody asks you to take the addition of two numbers and then find their remainder, and these two numbers are big numbers, so finding the remainder of a very large number, takes a lot of computational time. So if I said, what's a plus b mod m? Well, it's going to take me a lot of time. Well, what's nice is due to congruency, all right, that would be the same thing as simply going, oh, okay, let's take a mod m first. Let's take b mod m. Why is that nice? Modulus spits out smaller numbers. The number is either going to be 0, 1, 2, all the way up to m minus 1, so it's much smaller. If I'm mod 5, if a and b are the order of thousands, a mod 5, and I'm taking mod 5, is going to be either 0, 1, 2, 3, or 4. So the worst that this could be is 4 plus 4. So if I said, what's the modulus of 10,000 plus 20,000? If I take the mod of 10,000 and the mod of 20,000, I'm asking really what's the mod, at worst case, of 8. It's much smaller. And then we take the mod. This is also true for products. If I would take a big number times a big number and want to do the modulus, well, just simply take the modulus of A, take the modulus of B, then take the modulus. Again, if we're doing mod 5, if A and B are 1,000, what's A times B? 1,000,000. So if I simply say, what's the modulus of 1,000 times 1,000? Well, if I did 1,000 first, I would say I'd have to do 1,000,000 and then try to find the modulus of 1,000,000, which is keep subtracting. I'm sharing 1,000,000 little Skittles until I figure out the remainder, right? Well, that's painful. But on the other hand, it says, no. What's the modulus of 1,000? It's easy to share 1,000. What's the modulus of 1,000? It's easy. And if it's 5, it's either a number between 0 and 4. And so the worst case scenario on the right would be the mod of 16. That's the worst it could be. Which is, boy, that's a lot more effective. So it allows us to do some really fun things. So, for example, what would be 4 to the 375th power modulo 3? Exponentiation is multiple multiplications, right? This second part says you can just take the multiple of every one of those bases, right? Now, if you wanted to put this into your calculator, the reason I wrote that is your calculator can't do it, right? It's not capable of doing that particular problem. If you would want to be interested in that, you could do things like maxima, and what would be 3 to, I think it's times. What was it, 375? There we go. It's too big. Doesn't fit on the screen. All right? And then take the mod of that. All right? Now, maxima is symbolic. It's not actually doing the mathematics. It's a string manipulator. So it can do mathematics to whatever precision to run out of memory. But if I try to do it in a calculator, right, you would get what? An approximate, because a computer can't store it. Right? So that is too big for us to even do. But I can do this easily, because guess what? All I have to do is say, oh, modulus, all right, what's the issue here? You're not paying attention to my pen now? Somebody steal my pen? Maybe you go away. You gonna come back? back. Let's cheat. Are you working? Oh, all right, now it's, maybe I need a new, it's Friday. Lecture notes, thank you. First test day, 301, 10 a.m. Today's the 9th. Yay. All right. This is easy, because this would be what?
Okay.
You gotta be kidding me. Maybe it's, let's see if it's a, yeah, it's 4 mod 3, which is 1, and then what's 1 to the 375th power? 1. And so the answer is, without any work at all, it's 1. All right, let's see if this works. Okay. Okay, so this is equal to 4 mod 3 all to the 375th power, which is equal to 1 to the 375th power, which is equal to 1. Hey, I don't have to do any math at all. Oh, well, I did math. Didn't have to do hard math. So it's a nice feature, because all of these modulus will always take the number and either spit out a 0, 1, or 2. So you don't actually have to do the big computational work. You just simply work on the base and then take the power to it, and then simplify it down. So that's a nice property of modulus in congruency, is you can actually move. I have 17. Let's move it down to what is it the same as? You're working in congruency. Pick what it's the same as. 17 is too big. If I'm taking mod 16, that's actually 1. Take mod 15, that's actually 2. So you just move it to where it's most useful when you on that particular modulus. All right, so we know how to solve these particular things and work and move things around, so it's kind of nice to do particular problems. Now, what are we going to work on? We now get to talk about what is a number versus a figure. One of those ones where you kind of sit there and ask, what in the world are you talking about? I scheduled 3 days for 4-1, 4-2, 4-2. So we'll do a little bit on 4-2, and then since we have break next week, 4-2 will be finishing up on Wednesday. One of the things that we deal a lot in is we do not understand that most of the arithmetic work that we do, the tools of what's the technique of addition? What's the technique of multiplication? Share and carry and add. What are you actually doing? Well, most of what we do when we do things like, okay, what is 12 times 13? This technique is, okay, what's 3 times 2? That's 6. What's 3 times 1? That's 3. This is actually a 10, so it's a 0 position. 1 times 2 is 2. 1. Now I add, and I get 6, 5, 1. And so 12 times 13 is actually 156, and we would write that in. This process is what's called a figure algorithm. It's an algorithm based upon the way you chose to write the number. And these algorithms change depending on the way you chose to write the number. And that seems kind of awkward, but the important part about this is, what is a number? If I focus on just simply the positive ints, these are the numbers. Those, that triple dot is not the number 6. Really fun, right? The one on the right's an ellipsis. All the other ones are tally marks. Numbers are literally collections of ones. That's what they are. Now, life gets hard if we deal with everything as a collection of 1. So what we tend to do is take large collections and replace them with a symbol. So, like, for example, this. What would the Romans do instead of writing a tally mark of 5? What do they write? They would write V. Instead of a tally mark of 10, what would they write? X. instead of a tally mark of 50, they would write L, which is why we're not having Super Bowl L. Because people with Super Bowl L, we'd all get confused since most people don't know Roman numeral 50. So we write, this is the first year that they're actually going to write 50 as in 50. Now it's kind of important as like they would do this. So the first version of these things where we would write symbols to represent block quantities, the Egyptians had it. Like a million was an astonished man. Like, ah, that's a million ones. That's what it was, right? And they would write these symbols and say, okay, well, what if I have, if 10 is X, how would I write 30? X, 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 because I don't want to write 30 dots, dot, 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 right? They'd write X, X, X. Every X is actually 10 dots. They collect them into one particular symbol. Now, Babylonians went to this and said, this particular thing is a figure. Now, could you think of the interesting algorithms that you could generate to try and add the figures based upon Roman numerals? Or what about multiplication? What if somebody wrote, say, X, I, and they have V, and they want you to multiply? You look at this, you're going to have to develop an algorithm to do this, right? Well, what does this actually mean, and how are things going? It's actually kind of interesting is, what does multiplication even mean? It means multiple additions. So could you imagine, write this as a dot, 12 dots, times 5 dots. What does that mean? That means I'm going to have 12 dots with another 12 dots, with another 12 dots, with another 12 dots, with another 12 dots. Every one of the dots of 5 represents that I have a block of 12 dots. That's what multiplication means. Now think of a process that does that. Well, I just gave you an algorithm for dot version. So you could have algorithms to generate it and do all this work. Now, what happened is with the advent of another type is the idea of what's called a positional figure. And these positional figures are going to be also called base B expansion or a base B figure. How does this work? Well, we all know what a positional one is, so we use it. Okay, 1, 2, 3. Somebody read that number for me. Read it out loud. Just literally say 123. What did you just tell me? You told me that you had 123, which is 100 is actually what? It's 10 tens. All right, try this one. Somebody read that one for me. 4,236, which is actually 4 10 cubes, 2 10 squareds, 3 10 6. Positional numbers, as you read them, that is what they are. And what we normally, when we write, we tend to only write the what. We have a base, which is telling me group sizes. And naming is normally all we name is when we write them down, we write the words of how many. I said I had 4,000, right? I actually say it, 4,000. I don't say 4236. I don't say 4326. I say that you have 4,230, which is actually 310, 320, right? 6. It's just a form of English. So all of the numbers that we have are really just positional numbers, and the way we say it fits it. Now, does it have to be group sizes of 10? No. Any amount of dots can be written as an a to the k, b to the k, plus, until we get down to a2b squared plus a1b plus, and then just simply a0, which is really b to the 0, which is just a bunch of 1s, right? And this is simply written in number form as ak minus 1, and we go down till we get to a2, a1, a0, but I got to say what the base group size is. So this form of figurate numbers, written as figures, is our base B. And what we get to do with these base B numbers is the algorithm that you use for addition. I wonder what it's going to look like. The algorithm that you use for multiplication. I wonder what it's going to look like. The algorithm that we use for exponentiation. What is it going to look like? But it'll be actually exponentiation of modulus. But we do not have to stay in base 10. The words that we use, we think we've been raised into base 10, the Hindu-Arabic numbers, and everything's base 10, and we write these particular things out. You're in computer science. What are the classic bases you work with?
Base 2.
2. Base 8, base 16. So 2, base 4, base 8, base 16, up to hex. You can go up if you want to, base 32, base 64, right? Babylonians, base 60, all right? And we actually do something in English, and when we speak a word, that actually causes an issue. That when I say it, it makes sense, and when I write it, it might not, which would be this. Say that. 102. You didn't say anything about tens. You didn't tell me 100 no tens in 2. Right? You just simply said, it's not there. I'm not going to say it. That's the classic approach to 0. It's not there. I won't say it. Well, can you imagine what it was like when there was no symbol for 0? Uh-oh. Is there a 0 there? Is this 110 and 2? Is this 100 2 tens and nothing? Is this 100 no tens and 2? I don't know. Is it, 12, which is actually, well, in English, we have unique words up to 12. But if we stuck truly to the pattern, it'd be 10 2, right? Like 13. I suppose they'd call it, boy, that'd be what? 2 10, 10 2. Boy, that would cause all sorts of fun problems. Because 2 10, do you mean 20? 30 versus 13. Isn't that nice? The word teen. I suppose we could do 2 teen is 12. It'd be 2 teen. 1 teen would be 11. Anyways, the Babylonians had this issue. Think about this in base 60. If you didn't know there was a 0 here, is there a 0 here, is there a 0 here, are they or not? It could be two things like this. Is this 1 times 60 plus 2? Is this actually 1 times 60 squared, which is 3,600, and then no 60s, and then 2? Or was it 1 times 60 squared plus 2 times 60 plus none? For us, what would we do? This would be 1 comma 2 in base 60. This one would be 1 comma 0 comma 2 in base 60. For our notation, this would be 1 comma 2 comma 0 in base 60. In terms of figurate numbers, that's what the numbers would actually represent. A group of 60 dots with 2. A group of 3,600 dots and 2 more dots. A group of 3,600 dots, a group of 2 groups of 60 dots, and then no others. The way they actually dealt with this is the scribes got annoyed. You would have to, as they would write things down, and so what they did is they developed a form of a 0 that's not a true 0. What they developed was this. They would just simply go through it, and then where there was supposed to be, there's nothing here, they would literally put, because they used a reed that was cut, so their impressions onto the clay was always a V shape. And so what they would do is just simply barely touch it. They would touch it and say, there's nothing here. See, that's a little nothing. So that little nothing is, there's nothing there, skip it. And so they had positions, and they had a form of a 0, but it wasn't a true 0. It was a please skip this spot. So, all right, the attendance will be a little bit of reading ahead. This is page 254, and it's example 12. It's an algorithm. Can you take, for example, this one is, could you do 300 to the 644 modulus 645? And the way they talk about it. How could you do this by hand? So how do you reduce it? All right. So let's get, except for the attendance. So.